Hey, Math 7195, welcome back. Here we are continuing on with Unit 8. We're still doing the comparison of two populations. In today's video, probably be a short one, we're comparing two populations where we have dependent samples. We often use this test in situations where we're testing a subject and then testing them again later. So it's sort of like a before and after comparison. So we have this dependence on the subjects where they're essentially in both samples. So that's what we're going to do here today. Let's get right to it. So inference for two population means when we have dependent samples. It turns out to be your basic hypothesis test for a single mean, because we have two populations, but our test subjects end up, say, in both populations. And that's how the dependence occurs. Suppose you want to know how a diet affects me. So you weigh me before the diet, and then you put me on some, newfangled diet program, and then after a few weeks, you weigh me again. And then we do that for a bunch of test subjects. Here we have a population of, the people that were before they were on a diet and the population of people after they were on a diet, but the people were in both groups. So the test subjects, there's a dependence upon the test subjects. The samples aren't completely independent of one another. We could do the same test without doing that. You just have a bunch of random people that aren't on a diet and compare them to a bunch of random people that are. But I think in that case, it might not be as reliable as following the progress of people, but it does introduce this dependence. In order to do this dependent sample test, again, we'll have to have, samples that are dependent, randomly chosen, of course, and we need that normal distribution condition. The test statistic is just a t-score, and our t-score, it looks familiar. It's just like the t-score that we had before with x bar. We usually have x bar minus mu, s over root n, and now we have d bar minus the mean of the d over the standard deviation of the d divided by the square root of n, where the n is the number of pairs that you have, and d stands for difference. So we're basically going to calculate the differences before and after, say, we do something. So my weight before the diet and then my weight after the diet, we subtract the two and we get a difference, and then we just study that single variable, called d for difference. That single variable has a mean, that single variable has a standard deviation, and we're interested in the mean difference for the whole population. We can also construct confidence intervals for these mean differences, where here is our formula for the error. It's a t-score times the standard error. A weird thing here is the n is the number of pairs, not the number of individual values that you have, and your degrees of freedom are just n minus 1. Let's try an example here. We're going to test out two software programs. They have great names, Software A and Software B. And what these programs do is they take images and they try to extract the text from the images. So it's called optical character recognition. One way that we could test the two software systems would be to grab a bunch of images from, say, our statistics book. So we scan the first 100 pages in, and we have photos of those. And then we feed those photos into, system A and system B, and we're trying to compare them. So we'll check to see how many errors each one makes when converting from the image to text. And obviously there'll be quite a few when you're converting math books. There's lots of symbols and diagrams and things, and a lot of times that trips up those character recognition programs a bit. So we'll count the number of errors that software B makes and software A makes. And I think I broke it down to per 10 pages. So in my 100 pages of text, I'm going to have 10 pages. And then I'm going to count how many errors are in each set of 10 pages. So in the first 10 pages of the book, software A made 47 mistakes, and software B only made 38 mistakes. And then in the next 10 pages, software A made 15 mistakes, and B made 16, etc. and so on. In the last 10 out of the 100 pages that were scanned, A made 40 mistakes, and B made 35 mistakes. This is a case where we have dependence because we're evaluating the same image using two different systems. So I have that first 10 pages scanned, and I evaluate it with A, and then I evaluate that same image with B. So the errors are dependent upon that. It's not like I used, one stats book for A, and then I used a, chemistry book for B. I used the same book, the same image to compare them both, and therefore we have this dependence. Rather than just calculating the mean of this group and the mean of this group and comparing the means, we will attack this as, because they're dependent, we'll find the difference between each set of 10 pages. First 10 pages, the difference was 9. The next 10 pages, it was -1. I did my subtraction of A minus B in that order. You can kind of see that it looks like A is worse. It makes more mistakes than B, especially when you look at all these differences being positive. We have a new data set here then, and we can punch those into our calculator in stat mode or put them into Excel, and we'll get a mean of 3.7 and a standard deviation of 3.234. I guess these are, errors per 10 pages. Our difference in error per 10 pages would be the units. Let's do this test here. Somebody is claiming that, where is the claim? It is claimed, I finally read it here, that B produces fewer errors than A. So that's our hypothesis test. Step 1 is figure out the claim. B has fewer errors than A. So the mean difference, then, if I'm subtracting it in the order of A minus B, would be that if B has fewer errors than A, then this would end up being greater than 0. We're claiming B is better than A, which means that the mean difference is claimed to be greater than 0. And it doesn't say fewer than or equal to, it just says fewer, and that's why I used greater than. This is kind of the tricky part here, is kind of converting that into the symbolic version. But then once you do, you just roll on with your, 8 steps. The claim doesn't have an equal sign in it, so it goes as the alternate hypothesis. And then the null hypothesis is that it's the opposite of that. Then we can move on to step 3, which is choose an alpha. In this case, I think we were told to use a significance level of 5%. So there's a 5% chance we're going to reject the null hypothesis, even though it is true. Step 4 is where we check our assumption. We sort of already did this where we checked to see if they were independent or dependent. We have dependent samples, and I think they need to come from a normal population, and hopefully it's set it somewhere in there. It says that you may assume that the differences are normally distributed. The way we can assume that is if A is normally distributed and B is normally distributed, then the differences are normally distributed. So you could check them individually, or you could maybe make a normal probability plot for your differences and see. With only 10 values here, it would be rough. You tend to need, around 18, 20 values before that test starts to be reliable, really. Yeah, so that was our other condition that we have, normality. This tells us we're going to use a t-distribution with our degrees of freedom are n-1. In this case, we have 10 pairs of data, so it'll be 10 minus 1, which is 9. Then we can move on to our test statistic. It's d bar minus mu sub d over s sub d over root n. Grind that out. We already have d bar calculated up here. It is 3.7. We're assuming the null hypothesis is correct. So this mu d is something less than or equal to 0. If we evaluate it at 0, it's the closest call between the two categories. So if it works for this, it will work for any other. Our standard deviation is calculated there. 3.234. It's a sample standard deviation, obviously. And n was 10. Having calculated this ahead of time, I ended up with 3.618, which is a somewhat weird t-score, possibly. It's above 2. However, when you have a sample size of 10, only 10, then 3 isn't really that weird anymore. On the t-table, you'll notice, if you look at the t-table, for the smaller values of n, you'll see some larger values of t. Step 6, figure out if it's left or right. Pick a method and solve the thing. This is a right-tailed test. How about we do traditional today? Even though I do kind of prefer the p-value. Before doing the traditional version, we're looking for a critical value. It will be on the right side. T with a subscript alpha, where the area to the right of that value is alpha. In this case, we chose that to be 5%. And now we need to figure out what this t-score is on my t-axis based off of 5%. And in order to do that, I need to remember that the degrees of freedom are still 9. So I'm going to look up 9 and a probability of 0.05 to the right in my t-table. Head over to your crusty t-table. It's a good workout. Look in row 9 for our degrees of freedom. And look in the column where we have 5% in the right tail. So our test statistic is 1.833. And that's our critical value. You notice that our test statistic is quite a bit bigger than that. It lands way up here somewhere. So it's in the rejection region. Step 7, we will reject the null hypothesis. So it was pretty weird. It was weirder than I thought. And then step 8 is our conclusion. We just need to figure out what does it mean to reject the null hypothesis. So I'm going back to my setup here. Rejecting the null hypothesis means I am supporting the claim. And we're doing so fairly strongly because we know the probability of our error is 5%. So we can say there's the sample data supports the claim. At alpha equals 0.05. That, OCR version B makes fewer errors than OCR software A. Of course, this again could be a bad way to test software systems. If you are never scanning math books and you're just scanning novels, then using a statistics textbook as our way to compare them might be flawed. So the whole test might be useless. It could in fact turn out that A is better than B if we have if we're scanning books that are complete text and aren't full of diagrams and special equations and symbols. But that's just that goes back to the whole idea of setting up your experiments well in the beginning to get data that represents how we'd be using these things. If you're an Excel person, to get this t-score here, instead of using the t-table, you could just say remember when you're looking for t-scores, it's t.inv. And the inverse function works to the left. So instead of putting 5% in, I'd put 95% in, and then the degrees of freedom. And you'll get a number very close to 1.833. In fact, the next digit's a 1. If you prefer the p-value method over this, we would just find the area to the right of 3.618. Why don't we do that in Excel? So doing this in Excel, we have this example here. I copied and pasted the question in. I copied and pasted the data in. I used formulas to calculate the summary statistics, your D-bar and your your standard deviation, just so you have this in case you ever want to do one of these again. And basically, I typed it all up here, just as we did it. to calculate the test statistic, you basically use your own formula. I don't think there's a way to do this using Excel as, actually, let's try this. Let's first do it. I did it sort of the traditional way where I use the inverse function here to get the critical value, and we compared these two values and we rejected the null hypothesis. That's how we did it when we were doing it in the lecture notes. The p-value for the test is just the area to the right of our test statistic. And there is a function called, t.dist.right. So I was able to go to the right of this value with 9 degrees of freedom. And you'll see the p-value is pretty small. It's smaller than alpha. So we come up with the same conclusion here. Reject the null hypothesis. Same conclusion. I think Excel might have an add-in that will do this directly for us without like having to do these functions. Let's take a look. If we go to our data and data analysis, remember there are some hypothesis tests in here. And one of them here, let's see, t-test paired two sample for means. That's what we're doing here. We're doing pairs. So let's see what this does for us. And it asks us for the two ranges. So variable 1, I'll input this data. Oh, why don't I do it like this? I'll take the label 2. And then I'll click this little box that says that I am including the label in my data. It'll probably make the output nicer. And then here's version 2. And in the null hypothesis was that there was no difference, or it was greater than or equal to 0 or less than or equal to 0. I can't remember, but the number was 0. So you have to put that in for our hypothesized difference. We want to do alpha as 0.05. And how about we just put our answer, let's just put it over on the side here and see what it gives us. You'll see that it gives us summary stats. Let's zoom in a little bit. So it gave us the means, which matched the means that we had over here. It gives us the variance. That's the square of these two numbers. It tells us how many observations are in each. It tells us the Pearson correlation coefficient. That's similar to, or we'll talk about that when we talk about linear regression. It tells us the degrees of freedom. And look, it tells us the test statistic, which is what we had here. That's pretty nice. It gives us the p-value if it's a one-tailed test, and it gives us the p-value if it's a two-tailed test. It also gives us the critical value. So it gave us these numbers here. And it gives us the critical value if it's a two-tailed test. So it's up to you to interpret this. We knew that this was a one-tailed test, so this is our p-value. And this is our critical value. That's pretty cool. So these are our 3 important values for this test listed right here. And Excel just spits those out for us. It only does this if you have the raw data. If you had the summary values, it doesn't work as well. Yeah, well, that's pretty cool. I'm glad we found that. So that was worth taking the time to do some Excel on this. I think I'm going to hit save on that so we have that in here. And I'm going to edit this to say, what was it called? Paired? Paired to sample? T-test paired. T-test paired sample means. And I'm going to change this to say dependent. And same with this one. There. Now this template's all set up and we did it in our video. Okay. We can head back to our lecture here. And I think that's it for this one. You can do some more examples of this. Yeah, in the lecture here, I just have a t-table. So that's it. We'll move on to other hypothesis tests in the next video. I hope you have a good one. Take care.